Yes, welcome students. Welcome back to the next recorded video session. So today we are going to discuss the computational models in embedded design or embedded system. Now, what are computational models in embedded uh, design or embedded systems? So here we are going to understand how the computations are defined in the embedded system. What kind of models are used in order to define the computation within the embedded system. So we are going to discuss here many computational models using which the computation can be defined inside the embedded system. So the different computational models used in embedded system design are as follows. So first thing is data flow graph, or you can also call it as data flow diagram. So DFG model, control data flow graph. So that is CDFG model. Okay, one is data flow model, another one is the control flow model. So next is you can also use the state machine model. Again you have something called as finite state machine model here, and then sequential programming model. This is another computational method or the model which can be used for design and building the embedded system. So next is concurrent processing model, is one more computational model which can be used for embedded system design. And last is object oriented model. Object oriented modeling can also be used as the computational model for embedded system design. So now in today's topic we are going to discuss each one of this in more detail. So first we'll try to understand the data flow graph or data flow diagram. You can call it as DFG or DFD. If you're calling it as DFD, then it is data flow diagram, or you can also call it as data flow graph model. Now what this model does is it translates the data processing into a data flow graph. So when you look into that data flow graph, you'll get the complete picture how the data is getting processed within the system. So now this data flow graph model is a data driven model. That means the program execution is determined by the data. Right? So hence it is called as data driven model. Now how the data flow diagram is written, or data flow graph is written. So there are notations used to write the data flow graph. So usually the processing or the computation in the data flow graph or the data flow diagram is represented by using a circle, and the communication between one process to the another process is represented by using the arrows. So if any circle or a process is having an inward arrow, so then we say so the process or the circle is taking the input data. And similarly, if there is an outward arrow from any of the process or a circle, it represents the process is producing some kind of output, and that output can be fed as an input to the another process or circle. So circle is the notation which is used to represent the process, and sometimes you can also use the oval also. So embedded applications which are very high computational intensive and data driven are generally modeled using the data flow model. Okay, so that is what, if the systems are high computational intensive and data driven systems, then they can be best modeled by using the DFG model. That means the data flow graph model or the data flow diagram model is best suited for modeling the systems which have very high computational intensive and or data driven systems. Now here we have an example. Say I have a computational requirement. I got to perform this computation. X is equal to a plus b and y is equal to x minus c. This is what the computation I got to perform. Now how do I represent this? By using a DFG model, data flow graph model. This is how. So A is one input, B is another input. Now what are the kind of operation or the processing is happening? This is what the circle, which is representing the processing or the operation that is happening. So plus, and so output of this, x is fed as input to the second one. So x is flowing and c is another input. So the data flow node is this. So what it is doing, subtraction operation, and finally what you're getting is the result y. Okay. So DFG model is said to be acyclic DFG if it does not contain multiple values for the input variables and multiple output values for a given set of inputs. Say if it is only one input like this, a single input like this, then it is called as an acyclic DFG. So if it contains more than one input, say for example this has, so in addition to a comma b, a comma d comma e comma f, if I write something like that, it has more than one input values for this particular variable, then I say it's a non-acyclic DFG. But if it contains only a single input variable and single output which it produces, then I say it is an acyclic DFG. So next, this is what is the data flow graph. This is one way of defining the computation within the embedded system. That is, hence it is a computational model. It is one computational model used for embedded system design. So now what is the other one? So the other one is the control flow graph, or you can also call it as CDFG, and all of you are familiar with this because you have written the control flow graph, or in general you can also, it's something like the flow chart. So even in the first semester when you're doing the C programming, you have written the flow chart for every program. So it's the same way. Now in DFG, the execution was controlled by the data, and it does not involve any control operation. DFG was not involving any control operation. When I say control operation, the conditional statements. So something like if else statements, or the looping constructs, while loop, for loop, because they all go with the conditions. Now in the previous computational model, that is data flow graph, so it was, the execution was only controlled by the data, hence it was called as a data driven model. So so DFG doesn't involve any control operations. So now control DFG model, so this one, control DFG model, control data flow graph is used for modeling the applications involving the conditional program execution. So the CDFG model contains both, so data operation as well as control operation. So in this model you can observe both. I cannot say it is only data driven model or the control driven model, it is both. So in this model you can observe how the data is flowing and how the control is also flowing. So both can be observed, whereas in the previous model it is only the flow of data, but it doesn't have any thing to specify the flow of control. So now this CDFG uses the data flow graph DFG as element, and the conditional constructs as the decision makers. So this is used as an element, but this conditional constructs or the conditional statements are used for decision making, and these decision makers decide how the data flows within the program. So this, and it contains both data flow nodes as well as the decision nodes. So whereas DFG contains only the data flow nodes. Now again we have the example, if flag is equal to 1. This is what is the conditional construct. X is equal to a plus b, else y is equal to a minus b. Now to model this, I require CDFG. So I cannot model it only by using DFG. Now how it is modeled using CDFG? So it's here. Now we make use of the diamond block in order to represent the decision making element. So here you have one diamond block, and this is, all of you well know this, so diamond block which is used in order to represent the decision making or the control node. So this flag is equal to 1, yeah, true, then you take A input, B input, and you perform this. So if flag is not 1, false, then you come and perform this data flow node. So now that means, so these two data flow nodes are control dependent on this control node. And one real-time example what you can give is, so this, so for CDFG is capturing and saving the image to a format set by the user in a digital still camera. So you capture the image, and when you're saving, I want to save it in a specified my own format, then I have the option of choosing. So I've taken the picture, so save it in this so and so format. That is what that it's making the decision. So I say save it in this format. So it has to do the saving of the picture in the same format itself. Next is the another important computational model for embedded system design is the state machine model. Now the first model that we understood was data driven model, and the second model what we understood was control driven model. So but it also models the data flow. Now the next model that we are discussing now is the state machine model, which is used for modeling reactive or event driven systems, now whose processing behavior is dependent on the state transitions. So how the system changes its state from one state to another state because of the transitions. And this type of state machine models are widely used in the industrial applications. So say the state machine model describes all these things, describes the behavior of the system with respect to state, events, actions and transition. Now what is a state? Any system you take it as the states, finite states, and the state of the system is defined by its current variables. So the state is the representation of the current situation. The state, any point of time, it defines the current state of the system or the current situation, or it expresses the current situation of the system. Now what an event does? An event is something like an input to the system, which is going to make the system transit its state from current to the next state. Now transition is the movement from one state to the another state. For a transition to happen, there must be an event. And what is an action? So action is an activity performed by the state machine after the transition takes place. Now again, this is the state machine model that I told. So again, in the state machine model, you have something called as a finite state machine model. Now if the system has the finite number of states, then it can be modeled by using the finite state machine model, FSM. Now we have taken the example of driver or passenger seatbelt warning in order to explain the finite state machine model. Say I can take you another example also. Say for example I want to consider the garage door opener. Now the garage door opener, the garage door, or even the house door, or any doors if you take, so as finite states. One is closed state, open state, opening state and closing state. These are the four finite states of the garage door opener. So and now the system can be modeled by using these four finite states. Now here I've taken the example of driver or passenger seatbelt warning as the example in order to model the finite state machine. I'm just going to model this as a finite state machine. Now when the vehicle ignition is turned on, the seat belt is not fastened. So within 10 seconds of ignition on, say you are turning on the ignition of the vehicle, and if it not fastened the seat belt, so within 10 seconds of the ignition on, so the system will generate an alarm signal for 5 seconds. So and then the alarm is turned off when the alarm 5 seconds expires, or if the driver or the passenger, if he fastens the seat belt, ignition is turned off. Say he has turned it on, the ignition, and he forgot to fasten his seat belt. Within 10 seconds there was an alarm signal, and the alarm signal is emitting for 5 seconds, and it continues emitting for 5 seconds, and then the next thing, alarm will go into the off state after 5 seconds, after this 5 seconds elapses, or if the driver or the passenger fastens the seat belts within that 5 seconds, or if he switches off the ignition again, and whichever happens first, in all these three things, and again the alarm will go off. Here the states are, these are the states. One state we have something called as alarm off, waiting state, alarm, and alarm on state. So the events are this. So these are the different states: off state, waiting state, on state. Now, and there will be the transition of the system from this state to the other state, alarm off state to waiting state, or waiting state to alarm on state, or on state to waiting state, or waiting state to alarm off state. So based on these events, ignition key on, ignition key off, timer expire, alarm timer expire, or seat belt on. So these are all the events which will make the system to transit from any one of this, from one state to another state, which is mentioned here in these three states. Now using FSM, the finite state machine model, the system requirements can be modeled as shown in the following figure. Here we have the example now. So I told alarm off is one state, waiting is another state. So the states are represented by using the circles, and alarm on is one more state. Now how the transition will happen here? Now ignition key is on, say alarm is off and the ignition key is on. So it goes to the waiting state and waits for the user to fasten his seat belt for 10 seconds. Now if the seat belt is on within that 10 second, or the ignition key is off, it will go back to alarm off state. So if the timer expires, so user has not turned off the ignition key, or he has not even turned on the seat belt, so then the timer expires, it will go to from the waiting state, it will move to the alarm on state and start emitting the audible sound. Next, when the timer expires again, it goes to the alarm off state, or if the user turns on the seat belt, it will go to the alarm off state, and even if he switches off the ignition, it will go back to the off state. So this is the finite state machine modeling. So these are so that means the system alters or switches between these three states at any point of time based on all these events. So next is the alarm on state continues until the seat belt is on, or ignition key is off event, or alarm time expires event, whichever occurs first. So the occurrence of any of these events transitions the state to alarm off. So the wait state is implemented like this using a timer. So this state, again this wait state, is implemented as one more finite state machine model like this. So the initially the timer also has certain set of states and events transition. So initially it is in the idle state. So when the load timer event happens, and the timer count will be assigned with the new count, it comes to the ready state. So when the event start timer event happens, so from the ready state with the action decrement counter, it comes to the running state. In the running state, so the timer starts decreasing. So when the timer reaches 0, so stop timer or the timer expires event, it will go back to the idle state. So action is set timeout flag and timeout interrupt. So this is again the finite state model for modeling the wait state, which was there in the previous state finite state machine model. For this wait, this is the wait state implementation using a timer. Now, and this is further explained. This state diagram is explained here. So as seen from the FSM finite state machine, the timer state can be either idle, ready, or running. So during the timer is not running, so it is said to be in the idle state. Now it is said to be in the ready state when the timer new count value is loaded to it, and it's said to be in the running state when it receives start timer event, and it goes to the running state. In the running state, it start decreasing the timer value, and the timer value, when it reaches the count reaches 0, it goes to the stop timer event and get back to the idle state again. Now we have one more example here, so which is an automatic tea or coffee vending machine. And even this can be again modeled by using the FSM, finite state machine model. Now the process, this is the diagram which you're seeing here, the finite state machine model. So it has 1, 2, 3, 4 states. So this is the start state. So coffee or tea vending is initiated by inserting a 5 rupee coin. You can see the states here. So state A, this state is wait for the coin. So this is the start state, initial state. So it is waiting for the coin to be inserted, 5 rupee coin to be inserted. And then once you have the 5 rupee coin inserted, event is coin insert, action is okay, it comes to this state, wait for the user input. Because it is coffee or tea, now user has to say whether he requires coffee or tea. If the user says tea, so it goes to this. Event is T button press, goes to the state C, and action is dispense C. So this goes to the state C. Now the system understands the user wants the tea and it dispenses. So dispenses the tea to the user and action is done. If user selects the coffee, it comes to the state D and then dispenses the coffee and action is done. Now when user inserts the coin and when it goes to the state B and waiting for the user input, if user cancels, what will happen? The action is coin out, just return back the coin and stay in the initial state for accepting the next coin from the user. Now and again this is explained explanation for this finite state machine model, that is automatic tea or coffee vending machine. Now here, so wait for coin, these are the states. Wait for coin is one state, wait for user input is another state, dispense tea is another state, dispense coffee is another state. So user inserts the coin, 5 rupee coin, so there is a transition from the insert coin state to the wait for user input. When user gives the input in the wait state, the cancel button press, so then again the key the action that happens is return back the coin and move to the insert coin state. If the user selects the tea button press or coffee button press, then the state changes either to dispense tea or dispense coffee based on what the key pressed by the user. Yeah, and I have another example here, that is and the well-known example which you people have already used, that is coin operated telephone public booth. Okay, so the coin booth which we normally used to call it as. Now again the calling process initiated by lifting the receiver, correct? After lifting the phone, the user has to insert a 1 rupee coin to make a call. So if the line is busy, the coin will be returned back to you and you are going to put the receiver back onto the hook. If the line is through, the user is allowed to talk for 60 seconds, and when is talking, if it is the 45th second, so user will be prompted for inserting another 1 rupee coin. If he doesn't insert, the coil gets disconnected. So the call gets disconnected after 60 seconds. Yeah, and this is the finite state machine model for the public coin telephone booth. So here it starts from the state A, it is in the ready state. Now when the user lifts the receiver, action is okay, it goes to the state B, waiting for the coin here. State B is wait for the coin. Now when the user inserts the coin, again action is okay, goes to the next state C, that is the wait for a number. Now when the user keys in a valid number, action is dial. action is dial, and it goes to the state D, that is dialing state. Next, now the line is available, event line is available. The action is monitor duration. It comes to the state E, call is in progress, and it is also what, monitoring the duration. Next, what happens if the timeout happens, disconnect the line and go to the state F. So that is called terminated. And then again what will happen, event place the receiver. Once the call is terminated, you got to place the receiver back to the hook, and the action is done, and again it is ready state for making the next call. Okay, and in between I have two more states here. Say we are in the state C, that is waiting for a number. So if I keys in an invalid number, so display error will come, and it comes to the state H. What is state H? Is invalid number input. And then again you got to place the receiver back, and you get into the ready state again. And again in the state D, that is dialing state. So if the fault or the line busy, display error will come, and it comes to the state T. So that is unable to make a call, and then it goes back to this state A, that is ready state. And again we have one more state I, that is out of order. Now if the phone itself is not proper, so it is not in the ready state, it is in the out of order state. Okay. Yeah, so this is the finite state machine model. You understood various examples. Next, so most of the time the state machine model translate the requirements into sequence driven programs. So that means if I want to write a program for all these finite state machine models, I got to write a sequential program, because concurrent program is not possible, because majority of the times they are